Okay, can you hear me? Can you see me? Okay. I decided to change the title of my talk. Okay. So the very basic case when we speak about local to global is the volume of GA mod GF or GA1 mod GF to make it finite. So G is a reductive group, of course, over F, which is number field or global field, doesn't really matter. And GA1, A is the adels of F, and GA1, as usual, is the kernel of absolute values of all characters, rational characters, so like the determinant for GLN to make it finite volume. And so this means that we look at the sometimes people write it like this, became a common shortcut. So you look at this and you want to compare it with f of 1. Of course, only the constants here matter. And so if we are working in probability theory, it's very simple because the volumes are always 1. But there's a more natural measure here.
Sorry, what is this f of 1?
Yeah, so just the volume. I just wanted to stress that the volume is this proportionality constant, because it will be better to look at it this way later.
I'm confused about this equation. What is
So f is constant.
F is constant.
Otherwise, it's 0, so it's uninteresting. Well, if it's a Cas form. Anyways, I mean, this is just a way to it will look better for. Sorry. Yeah. So there is a standard measure that one needs to employ, but otherwise, then this question is meaningful. And of course, this is a venerated question. I won't get to all the history, but I just want to mention some features which will play a role in when we discuss the real thing, so to speak. But this, of course, is a real question. It has a lot of contents, arithmetic contents, which I will not touch. But so, as you all know, so already for tori, this is a non-trivial computation done by Ono, the father, and then for split or quasi-split, it was done by Langlands. Now, in fact, if the group is, you can somehow put in your fingers, so to speak, you can compute these things, and that was only done in many cases. I mean, there's of course the famous book of Wey from the 60s. But then you ask what happens if the group is, you know, simple, simply connected, adjoint, and so E8, right? So that's, you cannot compute it by hand, so to speak. But Langlands had a very nice way to treat the split or quasi-split to reduce it to the Levy, or in this case the torus, and then the issue is just to relate inner forms using Eisenstein series.
One of the great uses.
Get back to them, of course. And then inner forms. So also he had an approach how to do it in general using the stable trace formula. And this was accomplished by Kottwitz in the 80s. Anyways, so I didn't even tell you what is the precise statement, but this of course solves the Weiss conjecture in this. I mean, he has several, as you know, but this one says that the volume should be 1 if G is simply connected semi-simple, of course. So that was certainly there's a lot of mathematics going on here, and if that's not enough, then more recently, Gates-Gorey and Jacob Lurie have some mind-blowing paper in the function field case, but that's certainly beyond my scope of mathematics. Sorry?
In the function field, if you quasi-split the Eisenstein series, will still give it to you. So the issue is the lack of the trace formula there. But
I mean,
suppose you want to do it the same way
yeah.
in the function field, another step.
In principle, it's probably doable. I mean, there's no intrinsic impediment to it this way. But anyways, I won't say anything about this paper. That's, you cannot teach old dogs new tricks in my case. Okay, so let's now consider some more other classical themes. Hecke's L function, or Hecke integral. So phi is now a Cas form on GL2, and I consider following Hecke this integral. And when we do the Fourier expansion, so let's take our favorite character, non-trivial character of A mod F. This is a torsor of F star, this set. And I just pick one and look at the Fourier coefficient as a function of G. It doesn't matter which psi I take because it's just a question of changing the variable here, and then this becomes, because of the cuspidality, it will become at least formally, WFT1 dt. It's always the Haar measure, of course, when I unfold, and this actually converges if under some condition on the central character, namely, so now let's say that phi belongs to the space of pi for some representation, and the central character is, let's say, absolute value with something very positive, then this will in fact converge. And this is the partial L function at 1/2, the standard L function, times the local integral. Okay, so that's an unramified computation. Assuming, so S of course is such that phi is Ks invariant. So this is GL2 of O V not in S. So roughly speaking, I want to say that this period, or this integral, modulo some small things, it's this L value at 1/2 times the Fourier coefficient. Yeah, also, by the way, psi has to be unramified, but okay, don't worry about these small details. Okay, so this is not real news here. One thing I do want to mention, which because I think it's somehow it went under the radar, at least that's my impression, is that you you might as well put here an n and put here GLN. 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 Put a trace. This is M and A. Amen. GLN. Okay, get the idea.
GLN at the top.
Sorry.
No, there. You got, I don't know why you have two N.
Pi
Cusp on GL2N, right?
Pi cos 1 GL2N, yes. Sorry, I missed it. 2N.
Okay.
Why is the, I guess many of the steps go through, but why does the integral of the Whittaker function give you a 1 half pi?
Right. So this is a result of bump Ginsburg Furusawa. Now, of course, the difference is that we don't have multiplicity 1, right? It's not a Whittaker situation. This is just a Fourier coefficient with an abelian unipotent radical. There is no uniqueness here, not for the left and not for the right-hand side. But you don't need it for the unmodified computation. This is a, I think, a remarkable observation. I mean, it's following, I should mention the names of Adrianov and Petetsky, Shapiro, and Rallis, who followed him.
So this is a statement about,
This is not the Whittaker period, then. It's some
Yeah,
other
okay.
period. Yeah, it's
No, it's just called W, just a letter.
so the abstract statement is if you embed pi into the space of functions transforming under this n in some way, and you integrate it over the upper GLNA, you always get the local L factor.
Right, so locally, if you start with an Rutherford situation, no matter what functional you take, which has this property, if you integrate it over the GLN, you get the L factor. That's exactly right. Okay, just mentioning. In fact, I know that some other people maybe in the audience working on these non-unique things, but I think this is still kind of not fully understood, certainly not by me. Okay, now there is another way you can generalize it.
It's special to the value up, right?
Well, you can of course put the determinant to the S here if you wish. I mean, this is not the issue.
Okay. Question.
When you exit, it's equivalent. What is
Yeah, so it means that this is a true equality up to probably I messed up the measures a little bit, but this is just whatever you want to make of it.
Is this known at what it gives at the ramified place?
No, so the ramified, there are still some issues here. I mean, this equality is true, but of course the question is
Well, yeah, what's there?
what's there? Okay, so as far as I know, nobody worked further on this issue. But more importantly, it's not clear what to do with it. I mean, you have two things which maybe are random, but they're related by an L factor.
I assume you can vary they know enough to vary the local at the ramified to show it's not zero, right?
yes?
Oh yeah, this is not a big deal, but okay. So there is another way to generalize it, and by the way, this also works for. I mean, I said F is a number field. I didn't say F is commutative, right? But this doesn't matter. Works for diffusion algebras. So far, okay. But now, so another. But so, although Joseph has some reservations, I will highlight this.
There's no global to local thing in this case, right? I mean, that last integral still somehow hides something. It's not, we don't understand it.
So let's pretend that everything was unramified.
Let's pretend everything's unramified.
Then actually this is an equality.
Yes, but somehow, okay, there's that constant, the Fourier coefficient.
Right. So I mean, if you don't understand this, then you don't understand this. But
How about the Archimedean place? Is that actually very
well, I mean, in the Hecke case, of course, it's okay.
No,
In the
saying
in this case,
the partial L function usually just automatically they remove the Archimedean. Do they know that the Archimedean place?
so in this generality,
Yeah.
I don't know. I don't know. Certainly, they don't treat it in the paper, but I don't know if it was just for convenience or I simply don't know. Okay, any further questions? Okay, so I want to highlight this because two periods are related by an L value. That's kind of the motto of this talk. Fine. So another famous case, which extends this, so you can extend it in at least two ways. One, okay, you put an n here. Another way is to look at, of course, at the so pi on GLN and sigma on GLN minus 1, CAS forms, and you look at the okay, maybe I'll use this notation, which is nice. And this again, so the same story. You get the Rankin-Selberg product times well modulo yeah, okay, I'm sorry about it's not the same notation. So of course now it's the real Whittaker. Okay, so it depends on the group. Okay, so this is the upper, I mean, unit triangular, whatever you call it. And this is a non-degenerate character. Picks up all the simple roots. So this is the unfolding, right? I should mention the names of okay. Shabaika. Petetsky should be one.
This theory is actually complete. It can be complete.
Sorry?
This is not a theory where we don't know what's going on at the random place. I mean, the definitions where everything makes sense.
Well, if everything is yeah, I mean, we have, of course, local theory.
But you want to use a formula like this. It's kind of important. You want to make an estimate about an L function, and you have no idea what this factor is. So Rankin-Selberg theory is in good shape compared to something where you're just saying it's only ever been computed at unramified places.
Yeah, and of course, things are better for case n minus 1. If you do n and m, then you get some less computable things, but the theory is in good shape, I agree. Okay. Okay, another important Rankin-Selberg that I mentioned is, of course, the GLN case. So now you have pi. Let's just stick to single pi, although you can do with two of them. Doesn't matter on GLN, and then you look at the phi1g, phi2g. Now we have the Eisenstein series. Which I will define in a second, and that will unfold to, so you get the pi1, pi2, or pi times pi check. Let's say pi1, pi2. and then the integral. Okay, here we have some section. Okay, maybe you want to divide by the center, doesn't matter so much. So this is kind of a degenerate Eisenstein series or mirabolic Eisenstein series. So phi is, by the way, Schwartz function in Schwarzbrucher function on AN, and if phi so it should look familiar. It's something like that. Okay. So this is like a theta function or truncated, and then you take the Mellin transform, like Riemann did, and integrate. Okay, up to. Okay, you have to fudge a little with the S here because I want the functional equation relating S to minus S to agree with the standard today. Okay, and this is just Riemann. I need a continuation here, just Riemann or Hecke or Tate, whatever you want to call it. And you get the Rankin-Selberg theory for GLN times GLN. So yeah, so what? So in particular, so when I take pi 2 is equal to pi 1 check, let's say that pi is unitary, then I can recover and take residue. Oh,
You really mean to say that the bottom is equal to the left side, right?
sorry. What?
But then you want to sign it.
Oh, I'm sorry. Thank you. Yeah, okay, so I didn't define this, but I mean, this doesn't matter. You can guess what it is. Just made in transform of the phi. And now I want to take S equals, okay, maybe half, so that this has the pole of the Eisenstein series is just a constant function, and I will get the Peterson inner product of phi equals the residue of the Rankin-Selberg of pi with the control gradient times, let's say the integral. Okay, let me write it like this. Okay, what is this? So this is obviously an invariant inner product, as it should be, and it's given by so this is locally for any things in the Whittaker model of the local guy, if you want. But okay, it hides here, of course, the value at 1, which is like the global Whittaker coefficient, and I take so P. so P is the group of everything which ends up at 1, the mirabolic, so-called mirabolic subgroup. And I take, of course, the right Haar measure. It's not unimodular. And the miraculous thing is that this, which the first time you see it, I mean, for GL2, you just integrate the torus, basically. And of course, this is the same as GLN minus 1. GLN minus 1. Why should this be invariant if you just integrate over GLN minus 1? But the famous theorem of Bernstein tells you kind of a priori that it's invariant, but in this case, it follows from this relation, which you don't need Bernstein's theorem to prove this. So that expresses the Peterson inner product in terms of the Whittaker model inner product, and that's certainly something useful. And we can turn the tables, and so equivalently, if you like, morally equivalently for sure, you can write the Fourier coefficient, or the square thereof, is 1 over this residue Okay, there will be some very innocuous fudge factors which I will ignore, and then you have the pi n phi check psi n. So this, remember, the group of upper unit triangular matrices, and this is the Peterson inner product. And what we take this Fourier coefficient and take its Fourier transform at psi. And of course, you need to make sense of it, but again, this is purely local. And the meaning of this, so in the p-adic case, so this may not converge absolutely, but it converges in the stable sense. So the limit over all u. So this is compact open subgroup. It's a directed set, okay, of the integral over u. Same thing. Whatever. This this is just the limit of that in the discrete topology. So it just means that there is some u naught that for each subgroup bigger than that, the integral doesn't change. So it's the best kind of. So it's stable. That's why I wrote this. This is kind of stable integral. So in discrete topology. And this is a directed set. In the Archimedean case, unfortunately, we don't have too many compact or open subgroups, but so you can make sense of it in the tempered case by looking at the integral of the derived group and then taking Fourier transform as a distribution, which will make sense at that point. Otherwise, you have to do some analytic continuation. Anyways, so I don't know a very smooth way to deal with it, but there is a way to make sense of it, and then you get this equality.
Can you explain why it's equivalent?
Maybe not. But morally, I think it should.
Just checking, you didn't.
Yeah, so I mean, so okay, maybe I'll just say in one line, and for GL2, what it amounts to is that you have some, yeah, it amounts to this relation. So let's ignore convergence issues aside. I mean, you have some expression like that. So this is a Whittaker function, and then of course you can write it as a so you after you conjugate it becomes psi of tx. So let's write it like that. Okay, I just conjugated the x and used the equivalence of Whittaker. And then what you see here is a Fourier inversion, right? It's a double Fourier transform. So this is the Fourier transform of this function at the point x against psi x, something like that. So you look at it as a function in this variable, and that should be the w at 1. Of course, this is hand waving. You have to justify this. Does it make sense? Okay. I want to mention some local things related. So, okay, as I said, the theme would be to always have some relation of periods, whatever that is good for. But somehow, I don't have full explanation of what's going on. Maybe Yanis and Akshay have better one. But whenever you have such a global thing, you always have some local counterpart. Of course, you have the local functional equation. And so let me just tell you what it means in this case. I mean, you can think about GL2. So this is how I like to think about this. So I mentioned that you have this inner product, this kind of miraculous inner product, which is not justified to be an inner product, but it is. And then you have a naive inner product. So let's just take a super Caspian representation locally, even of GL2. So this is a local non-Archimedean field. So we have this, what I wrote before. So everything is, so it's automatically generic. So let's look at the Whittaker model. Okay, so it's inside the space of W, which have the right equivariance. We fix our non-trivial favorite character. There is a unique such model, and for pi, of course, G acts by right translation. And so you compare this one with kind of a naive one, which you can do for any group, because since it's Caspidal, the Whittaker will always be compactly supported mod n, or mod z n. So just integrate like this. Okay, so these are two inner products. They are non-trivial, of course. And so they must be proportional. So what is proportionality constant? So that's in fact what the functional equation tells you. I didn't write down the functional equation, but the consequence of functional equation is that the proportionality constant, let me write it down. So let's say this thing. So I will write and then explain. Okay, the notation will be for any GLN, it doesn't matter. So T over N, Q to the 1/2 F by pi, 1 minus Q inverse over 1 minus Q to the minus T. Oh, it's the other way around. Okay. Of course, in my handwriting, I cannot distinguish between these two, but let's pretend that it's this one. So what is this notation? So T is the size, so it's like for torsion, size of the group of unramified characters such that pi twisted by chi is isomorphic to pi. And okay, n is the GLN, and the f pi times pi check is the conductor of the functional equation, or the epsilon factor. So that's kind of the beef of the functional equation. There's nothing special at the point half. I mean, you don't need to worry about the the thing with modulus 1 because it's just 1 essentially, because it's pi tensor pi check. But you still have some, this is the content of the functional equation. And then, yeah. Now, so it looks kind of random, but the point is that this proportionality constant, if you think about it for a second, it's nothing else than the formal degree. So that tells you that the formal degree, of course, you have to normalize the measures. I'm always a bit, I'm sweeping under the carpet these details, but this is the same as the formal degree. So, okay. For the right measure. Of course, there is some assumption on psi, and psi determines the measure. Anyways, this is some unimportant details, but that's what you get. For instance, from this you get a lower bound on the conductor, because the formal degree is always divisible by that of the Steinberg representation. But that's kind of a kind of different input.
Why is that?
Why is what?
You said the formal degree is always.
Yeah, the formal degree is always divisible by the formal degree of the Steinberg representation. That's an old result of how before you were born. I'm sorry that I started to sound like you're dead, but and it comes from the fact that this is the coefficient of in the germ expansion of the zero unipotent term. Okay. Okay, so now, okay, so we have all these very well-known things, but now sometimes, so Rankin-Selberg integrals are kind of special. They are few and far between, so to speak, but these period integrals somehow they abound, and you want to make sense of them. So let's do some twisting things. For instance, let's consider. Back to the original case, we considered an integral.
The very first integral you put down, bumped in somebody.
Yeah.
Does that give the function equation also from that one side?
I mean,
Get anything like that?
it's unclear because you don't have uniqueness, so it's just unclear.
It's just an identity in terms of an integral representation which has not been used.
But you can get the global, right? You just can't get the local.
Yeah, so it's not clear that there is a local theory there. It was certainly not developed as far as I know, but it's unclear that it exists.
Looking from the other side.
Global functional equation. How? Isn't that added bump Ginsburg and Kurosawa? You can get the
Oh, the global functional equation.
global functional equation.
Did you
How?
I have to think about this.
You
Is it
don't
clear?
see the bad factors for one thing.
even assuming that just for the partial L function.
Yeah, I don't know. So, is it?
And that function, nor is the function that you wrote down manifestly S to minus S in there.
That's why I asked you to put in the S. When you put in the S, it's obvious.
No, I have to think about this.
Is it a
honestly.
useful integral representation as well?
Okay, we are on the record, so I cannot. No, I don't know. I just don't know. But I think it's underemployed. Let's put it this way. But yeah. So now I want to consider back to the first example, but just for GL2. So we had this thing, right? Hecke had this for us. Okay, what happens if you consider the non-split torus? So one thing I already mentioned this Eisenstein series, this kind of Riemann-Eisenstein series, if you like, or Hecke. So if you take this Eisenstein series that I had before, remember this is a degenerate Eisenstein series, and you integrate that on your, so this is for GLN. So T is a torus, let's say corresponding to, so like E star, and E over F is degree n extension. And you take the Eisenstein series on GLN, so a torus in GLN, and you just integrate this Eisenstein series, nothing else. Okay, always with this one thing. So this is, so that's basically that's the Dedekind zeta function, right? So that's the classical computation. So for GL2, I mean, so it's kind of good and bad. Okay, so you get this Dedekind zeta function, which you can factorize if you wish, but it's unclear that what can you do with the Cas form instead, right? Because this Dedekind zeta function, so it will be, okay, let's say the usual zeta times the Dirichlet. But this is not a standard L function of the Eisenstein series, so to speak, because I mean you have this twist. So it's unclear what you would get if you plug in Cas form instead. I mean, let alone prove something, but how do you formulate? I mean, in automorphic forms, you never do computation that you don't know what is the answer to begin with, right? So how do you formulate things? So nevertheless, if you square it,
I think Langlands, when he computed the constant term of the Eisenstein series, he didn't know what he was getting, and he had to interpret.
okay, but many years have elapsed, so the standards have changed. Okay, anyways. So the nice thing is that if you square this thing, then what you get is the L function of the, so this is degree 2. If squared, it's degree 4, and it is nothing else but the L function of the base change. Well, in this case of this induced representation, of course, the base change from F to E. So this is some beast on GL to E, and it has its standard L function, which is now degree 4, and so this is just a formal computation. So that somehow suggests that there is some, so for Cas forms, so what about Cas forms? Now you get a meaningful, okay, so this is the torus embedded in the GL2, and okay, so again, of course, and by the way, this is the same thing as, so this is the base change L function. But if you put a character here, then somehow this collapses, and what you really have is something like that. Anyway, so that kind of would be an expectation. Of course, now we know that, and for many years. So such a relation, which of course you need to make precise, and I will say something about this, was of course proved by Walsh-Perget many years ago. I mean, I guess in the 80s. And there is a follow-up, there's a lot of follow-up. So he used the theta correspondence. So there are also some similar problems. I will maybe discuss some of them. And subsequently, So it was reproved by Jacquet using the relative trace formula. So there are advantages and disadvantages to each method, as usual. Okay, I will say more about this later for sure. I want to give another twisted example. So that's of course a special case of the Gross-Prasad type integrals, the conjecture of Ichino-Ikeda. I will return to that. But I want to mention another twisted version. Actually, I want to compare two twisted versions of the Rankin-Selberg for pi times pi. So one is kind of a naive one, if you like. If you take, so again, E over F is a quadratic extension. And let's say phi is a cusp form on GLN of E, the restriction of scalars, the F points of the restriction of scalars, if you like. And so again, I have some representation pi here. And I take the integral of GLN AF mod GLN F. Okay, so this is the twisted analog of inner product, right? And just more or less formal, just like the usual Rankin-Selberg, what you get is the LS, the residue. So you have a theory if you put an Eisenstein series here, and what you get from it is a residue of some L function, which is called the Asai L function, times the integral. So Pm is the mirabolic of Fs, mirabolic subgroup of GLNF, just like before.
Since we have you here talking about this, maybe you could say a word about your own theorem about the non-negativity of the L function at a half, which comes from any square, but for which you have, with Rallis, the complete characterization of those. There will be no non-negativity. Can you say a word about it?
I mean,
Because I think that's kind of one of the most interesting theorems.
well, I kind of mentioned it here without it. I mean, the fact that this is a local counterpart, but it doesn't matter. The fact that this epsilon factor doesn't have a sign here, or doesn't have, I mean, basically the sign of the modulus function of the epsilon factor, so locally, is reflected by this positivity here.
Yeah, but the issue is, in Jacquet's proof, and in Weizmann's proof, it's clear that the L is the square, and you actually know what the square is.
For this, yeah. Sorry.
On the other hand, you have all the cases for which, every single case for which we know the non-negativity other than a numerical calculation, for cell dual form from GLN, standard L function, is contained in your paper with Rallis.
Well, I mean, the thing is that
When you say a word about how you use Eisenstein series and residues and where you get the sign from without.
yeah, okay, maybe let's do it now because this is kind of too. It's not what I planned, and.
I'm ordering.
Okay, so for next time.
It doesn't have to come today.
Yeah. Okay, next time. Okay. I'm sorry, I'm not 100% well, so I hard for me to focus. But yeah, so this is just a twisted analog, but there is a less clear analog. So what happens if we consider I mean, I will talk about my results. Don't worry, I'm not shy. But another one. So consider a unitary group instead of.
I think everybody was born by the time you put that in this room. Not that.
Instead of GLNF. Okay, so a unitary group, which is it's an outer form of GLN. What happens then? Of course, you have many unitary groups, but okay, pick your favorite one and integrate your class form and see what happens. So the thing is that it's more complicated. I mean, you don't have. So the nice thing here, this was kind of. Though you could do some extrapolation, you put some Eisenstein series, which looks kind of out of the blue. I mean, a priori, posteriori we'll get used to it, but you put some gadget here, which doesn't seem to be natural, at least at first sight, and then with that you compute. Okay, then you take residue. So you have another variable in particular to play with, but in the unitary case, it doesn't seem to that this method works. I mean, maybe somebody will come up with something, I don't know, but it doesn't seem that it works. In other words, you cannot extrapolate it in some or interpolate it in some family or whatever you want to do. So nevertheless, so this is so Jacquet came up with the relative trace formula in this case. So that's, again, this is history. Okay, maybe everyone was born, but it's not that recent. And so let me tell you what is the outcome, and then we'll see. So first of all, the answer is that, okay, so I consider this unitary periods. So this is some unitary group. Which splits, of course, over E, so everything is with respect to E. And it's non-zero, so the first thing is that this is non-zero for some thing in the space of pi. At least this implies, but essentially, if and only if you're allowed to change the unitary group, that pi is a base change. So that shouldn't be too surprising. In fact, this is not a difficult result. There's a nice trick. Right, from GLNF, thank you. Quadratic base change. Sorry, that becomes invisible a little. So that shouldn't be, and that, by the way, is the same thing, but that's somehow kind of a different thing that you don't maybe absolutely need for that, is that pi is isomorphic to twist under the, I'll call it tau, under the Galois group. So that's, of course, Arthur Clausel. Right. So right. So okay. If I want the precise condition, then there exists a unitary group. In fact, it's enough to take the quasi-split. Enough to take. But it's not a priori clear. So that's the qualitative statement. The quantitative statement is that you can make sense of this integral in a way very similar to the, so this is a unitary group, in a way very similar to what I described at the beginning, as if it was like coming from Rankin-Selberg, but okay, there is some twist, but so let me try to say it more precisely. I won't give every small detail in the statement even. So yeah, and then I will say some words. So the statement is, if I can find it, yeah. So it's 2 times the L function. So remember, now pi is a base change. So pi is let's say base change of pi prime. So pi prime is Caspidal on GLNF. I assume that my pi is Caspial to begin with, but that's stronger than saying that pi prime is Caspial, in fact. And in fact, pi prime is not unique. You can twist it by the character, but of course, the statement should be invariant. But this is important. And so what you have here is the twisted Rankin-Selberg of pi prime. So this is.
Can you say a word about this partial L function that comes and goes? In the Rankin-Selberg theory, we don't need to put that. In some theories, which are these Ginsburg miraculous Rankin-Selberg, they usually only work in unramified places and locally nucleic. It's very important if you ever want to use this, as I found many years ago, if you want to say use it to bounce towards Riemann, you need to know every place. So in Jacquet's work, my experience is he never leaves anything untouched.
Okay.
In his case, it would not be LS, that's why. Are you
Yeah.
doing that just for notational?
Well, I didn't finish the sentence.
Okay, sorry. But
Okay.
I think give him credit because he really always works everything out.
So, so now there will be the local function. I mean, this is meaningless, right? Because it should depend on phi somehow. It should be proportional. And what you have here. So, okay, I'll first write it down and then explain. So you have some functional which is built of local things. And what are these local functionals? So these are local functionals on the Whittaker space. But unfortunately, they are not as explicit. I mean, okay, the next stage is to compute them. But first, let's just write a formula. Even just that the board can suffer. And here. Okay, so this is the statement I'll try to. So look at pi prime f prime. I'm going to define for you, but not directly, because that's the best I know, to these local functions. So x, by the way, so this is unitary group of Hermitian form x, pertaining to x. And let's look at pi prime f prime. So f prime is some test function locally. This is an element of just endomorphism of the vector space of pi prime. So, which I identify with, I mean, everything is kind of finite rank, so you can identify it with the space tensor itself or the dual, but I take the Whittaker realization, so it's some element here, and now, so it's legitimate to apply this. Remember, this is a space of functions, honest and good functions on the group. I can just take the evaluation at the identity and the W naught, the longest val element. So this is a distribution of f prime, if you like. Everything is local. On the other side, what I have, I can do the same thing with pi of f. And okay, so one variable will be the just evaluation at E, and another variable will be this. Okay, for some reason I call it, okay, let's call it Lx pi prime. So
this refined statement was in your work with pi.
no, I will say. So this is something that I want to. This defines. So this defines Lx pi prime. Well, everything is at V. I don't want to carry out the V all the time. It's not kind of, I mean, you can, of course, if you're Peter, then you can complain. I mean, can you go to the supermarket with that definition? That's, of course, it's a valid, but at least.
S contains a ramified, what is
Yeah, S is as usual. So pi, your vector is phi is ks invariant. This is, and maybe there is a psi here which has to be unramified. Yeah, this is. Goes without saying. So this defines Lx, but I didn't define, of course, what is f and f prime. So f and f prime are related. Is it visible, actually? Maybe not. So f prime and f are related, and the transfer somehow depends on x. So there are some matching conditions, which are geometric conditions, which I will not write down. There is a transfer factor and some orbital integrals which make things match. And this gives you just a definition. I don't want to say recipe, but just gives you an existential definition. Of course, so I hope at least the statement is not less than meaningless. And
2 means 1 for each base, one for each choice.
Right on, yes. So the 2 is very important. In fact, the 2 tells you that you cannot prove it by ranking Selberg. I mean, there's no way that you could get 2 with algebra, right? Or with analysis, sorry. I mean, you did. I mean, like, that's what actually that ties it to the first. I mean, the thing about the volume, right? I mean, the Tamagawa number of a unitary group is 2. So that's really where the non-split comes from, and there's no amount of ranking Selberg unfolding I can do to get these 2. Yeah, so just for the record, so basically it's a theorem of Jacquet, some final touches by Feigon and Omer Offen, and also Rami Eisenbad and Dmitry Gurevich, who contributed for the matching at the Archimedean place. Now, in fact, the thesis of Bauch-Chernigov was about the fundamental lemma for this case. Later on, it was reproved by Jacquet by other means, and he extended it to matching, etc. So there's a long history, but Jacquet is basically the founding father here, and wrote many papers, of course, some with his students. Anyway, so this is. So, in some sense, because it does give you factorization, you have to. There are some small details that you have to not overlook. Namely that these local factors, they depend on the pi prime. Okay, so pi, remember, is a base chain of pi prime. Globally, there are just 2 choices. You can ignore this because it's just a twist by omega, this eta EF, what they call, that's the quadratic character, of course, pertaining to EF by class field theory. By the way, this doesn't have a pole because pi is cuspidal. That's exactly mean that this value is well defined. But locally, of course, there are many choices. I mean, finitely many, but still, for the, you see, I mean, what you're supposed to get here, whatever you do, you're supposed to get an invariant functional. And there are many invariant functions, finitely many, but many. And you have to pick one, and the choice of which one depends on the global data, right? Because pi v prime, you know it because you know pi prime. But if you just look at pi v itself, you couldn't tell what is pi prime v, because there are many. So this somehow nicely picks up the functional. And already, in fact, you know, even if you don't understand what's written on the board, which is, you can be excused, then the thing is that this factorizes. That's already a statement here, because it's unclear, again, because you don't have a priori uniqueness, so it's unclear that it would factorize into local functionals. So that's kind of part of the statement. Any questions so far? Yeah.
I mean, should I think of this as being a sum of 2 things at that, or should I really mean?
So one way is to think, as actually said, I mean, the fact that you have 2 pi prime, but the other even more naive thing is just to look at n equals 1 and to say what I have here is the measure of, you know, E1, the torus E1, which is 2 in the right normalization. So it should come from somewhere, and that's where it comes from. But I don't have a good kind of. Yeah, no, that's all I can say. Of course, so the method here is the relative trace roller. I said nothing about that, but and probably I will not, but because I want to move to other things. But
Maybe you could say a word about in this relative trace formula, the assumption in how the general setting would be that you have a subgroup H with what properties of G. I mean, this is a special case.
sure, Yeah, so, okay. So so in this kind of cases, it's kind of baby cases that, so you have, let's say, a quasi-split group G, and you look at the Kuznetsov type which analytically is very pleasant, at least. You just integrate the kernel in the two variable. Or very compact. Subgroup, that's always nice, and quotient rather. And what you compare it with, so okay, so this is, let's say, one group, and then you have some G mod H mod N psi.
Okay, so in my understanding, what's the assumption on H then?
Right, so I think that, so in this family of examples at least, so G would be the restriction of scalars of H, as well as the restriction of scalars of G prime, in fact. But okay, but they are related somehow. They are not the same necessarily. They could be the same, and so there is kind of a Cartan involution or something, which relates them, and.
So the H needs to be the fixed point of evolution.
Yeah. Okay. So the,
It's your case setup.
so right. This is even more special. Yeah. I mean, there are always some subtleties. I mean, this case at least is uniform enough that you can make sense of it for any, basically, H, but with some details. Okay, so maybe it's a good point to take a break. The Barcelona game also started. So the Ichino-Ikeda conjecture, which is very important, and at some point I will write it down, but maybe I will not do it right now or today. Instead, I will write kind of a watered-down version of it in a special case, but it has a feature that it works for any reductive group. I mean, conjecturally. So, but and of course, I mean, sometimes I don't mention some people's name, so don't take it as an insult. There are, of course, many people and ideas involved here. If I don't mention, then please excuse me. So the conjecture is about Whittaker coefficients and in the joint with Mao. Mao. And but as a prerequisite, we need to say something about the Arthur's conjectures. So G will be quasi-split for this conjecture, and so Arthur conjectures, there is more than one version of it. And I will take the following version. So the idea, and that, yeah, I should say this is certainly in, yeah, it's an actually version. Let's call it the version. So the point is that we're talking about not just kind of an abstract multiplicity formula, but a real physical decomposition. And this is an important point. So phi is some parameters. I won't say too much about these things. They should look familiar. So these are the Arthur parameters. This is the Langland's hypothetical group. And which should parameterize Caspar representation of GLM. I mean, it's n-dimensional representation, it's this Tanakian formalism. So everything is very hypothetical, but somehow there are several layers of hypotheticality. So of course, this is This is highly hypothetical. Arthur likes to say this is the last theorem which will be proved in automorphic forms, the existence of this group. Arthur. The last theorem in automorphic forms is the existence of this group, but or something like that, which of course, because it implies everything else and probably cannot be. Anyways, but there is more stuff can be said in the function field case. Anyways, so there is, if you believe this formulation, there is some canonical decomposition according to parameters. So these are output parameters. And I emphasize canonical or kind of physical, not just. I mean, Arthur would never formulate it like that because he takes traces, and once you take traces, you don't see any canonicity in life. But there should be some canonical decomposition. And of course, it has some properties, so it should match Hecke parameters.
I don't understand. Arthur tells you that if you decompose, he gives you the discrete spectrum.
Okay, so I can put.
What are you saying?
I'm saying there is a canonical decomposition of L2. You cannot take traces and have a heavy canonical decomposition.
I'm saying, he gives a description of what should appear in the discrete spectrum under the regular decomposition, right?
Yeah, sure.
So what are you saying more?
I'm saying that there is a canonical space. Arthur gives you multiplicities, if you like, in the best possible
Yeah,
scenario.
that's appearing in, I mean, you have a decomposition there, and you decompose it.
But what if I have overlap?
Now, each guy occurs with some multiplicity. I mean, you decompose it into irreducibles. You can do that. It's unitary. I don't understand the discrete spectrum. If you
No, what I'm saying is that two things can coalesce. I mean,
So what if you have not discrete? It's just a two.
right, okay, at the moment I wrote discrete, I wrote L2, but in fact you can, this is a simple step. If you just impose something, then you can get to discrete. So that's not the issue. Because, I mean, the Hecke parameters don't tell you all the story. So unfortunately, I cannot make, and as far as I know, nobody can make sense of this refined conjecture, because you know the telltale of a good conjecture is that it's unrefutable, right? Just joking.
don't have to argue with me about that point. I'm just saying that in a concrete situation, he's telling you, say, if you're a classical group, he's going to tell you which guys appear with what. He's going to give you a formula for the multiplicity of the discrete
Sure,
occurrences when you decompose it.
sure.
And they occur in GA over GF. I'm not sure what you're saying. What more
I
do you
think
want?
he's saying that there is a never final decomposition.
I will give you example.
It's a
Okay,
separate issue, but
no, but that's the point here,
what
because
else do you want?
There's a final decomposition which is canonical in a way that we cannot.
I don't know.
okay, I mean,
It shows up in Laforgue, for example.
exactly, that's what I wanted to mention.
Economical beyond your wildest dreams.
So Hecke operators,
Economicalness that you ever thought you could.
Hecke operator is not everything on the table, and Laforgue.
You don't have to tell me that the Hecke operator doesn't tell you anything, but that notion of multiplicity, you decompose that irreducible. Imagine that's GA over GF is
Okay, maybe,
compact. Let's suppose that's compact. There's a countable decomposition of irreducibles in that space, and you're going to give me the multiplicity with which each guy occurs. That's not
okay, I think it's a dialogue of the deaf. So maybe I'll give an example, and that will give you. So if you're looking at GLN, then of course there is no problem. I mean, in as much that we don't know what are Caspian representations, right? But this decomposition into spaces, I mean, you cannot ask for anything better because every representation is multiplicity one. You
You're
have,
saying here, nothing.
right.
Okay. Keep going.
So in other words, this is just the Langlands thing that this formalism, nothing more. However,
I mean,
okay, no,
giving
this
the
is
answer in
okay.
terms
Plus
of values
plus
of
residual.
L functions
Sorry.
of whole, that's true.
Sorry?
Keep going.
Yeah, okay. So the GLN, the cuspidal part, I skipped a step, but the cuspidal part is no, and also the discrete part, in fact, in this case, is not a problem. So the issue is not, you cannot see it in GLN. However, if you go to SLN, so you can do two things. Well, if you have a function on GLN, I can just physically restrict it to SLN. It can be 0. But it gives you, so that means that this induces some decomposition of L2 of SLN. Let's say the cuspidal part, because the issue is not about anything else. So I have a decomposition of SLN according to things in GLN. So pi is a cuspidal on GLN, and then I just do this restrictions of the pi, so to speak. Now this thing is no longer irreducible, so it could be reducible. It is multiplicity 1. I mean, it is multiplicity 3, but it is reducible, and it can happen that different pi's have isotypic, or rather, I mean, these two things can be isomorphic just as a representation of SLN, because it doesn't see the, I mean, so the real decomposition is with respect to GLN, or if you like, the adjoint group. So that's some extra symmetries that you have here.
And what does Arthur say?
Well, Arthur would not be able to, I mean, so let's say that Arthur just give you multiplicity formula which counts how many things are isomorphic. But I want the actual direct, so I really want these kind of canonical spaces which can only come from GLN. Why do I make this point about this?
Couldn't they cancel out? For instance, it's the same different representation, distinction is the same thing.
Yeah,
Can I say
that's what I'm saying, yes.
You can say this is, you can have, if you have a general group, you can have two Galois representations.
Yeah.
So it's an every Frobenius conjugate.
Yeah.
But then, so the point is you should be able to, they're a two-dimensional space in automorphic forms. You should be able to match them, one with this one with that one. But we at present have no way to do so.
No, I'm not
So I
arguing
think-
with that physical.
But
magic.
that's what I think Erez is referring to.
Yeah, so you have some extra symmetries, and then you have multiplicity 1.
I
Or
think it's in terms of how you realize it.
okay, but of course, in this case, or I mean, you can always use the adjoint group to have these extra symmetries. That's kind of a no-brainer. But there are sometimes more than that, right? And this is less clear. But in the function field case, so the work of Laforgue, Vincent Laforgue, gives you some decomposition. Well, maybe it's not. I mean, certainly it's only for the cuspidal part. So he gives you some kind of spaces which are kind of. I mean, they should be the right thing, and he has these extra symmetries. But this is very kind of function field thing. And of course, it's compatible. So as this example shows, I mean, these spaces should be compatible with, you know, when you move to isogenous group and stuff like that. Okay. So why did I go to trouble except to tease Peter? Because when you formulate conjectures,
I think you answered in the case of orthogonal groups, or wherever they have the fundamental worked out, there's no LF is needed. It doesn't need the group F.
oh well, okay.
I'm just one point.
There is-
theorem is telling you can read Ramanujan from it, for example, if you're willing to compute all these parameters. Everything there is explicit.
Okay, let's distinguish between kind of ideal world and what you do in real life when you don't have this and you want to formulate your theorems.
And when he proves anything, he doesn't have to look at LF.
So you can substitute this, sure, but I just want to first set the picture. And of course, for classical groups, you have the, so just like for GLN, you have the luxury that for classical groups, multiplicity ends up eventually, you don't know it a priori, but it ends up to be 1.
Yeah,
Which renders all this discussion and our dispute superfluous. But I want to make a point that so when you now I want to formulate this conjecture for Whittaker, but there are variants of this. So it's a kind of refined case of
just to clarify what the issue with LF is if I give you an automorphic form on GLN, and I ask about its tensor powers, give you some number of them, and ask whether that L function has a pole or not, that group LF supposed to answer that? But that's a question.
Okay, I mean, LF, it gives you the parameters. I mean, but okay, let me just get to the point. So let me consider this Whittaker function. Okay, so the Whittaker coefficient, excuse me. So I pick my psi non-degenerate character on the maximal unipotent.
Okay, what group we know?
So for now, any quasi-split group. And I want to relate this, or rather the square, to the adjoint L function. So here is the conjecture. So there will be some fudge factors here. And yeah, so, okay, I will first write it, and then if I'm not interrupted in the middle, I will say something. Don't hold your breath. So it's very much like what I wrote before for GL2, if you remember. But somebody told me that I forgot this factor. So if I did, then please correct it in your notes. Okay, so here actually we're working like probabilists because I will divide by the volume. So the volume is 1, but it doesn't really matter. Yeah, so what's going on here? So phi is in the space of pi, and okay, so I should have said this before. So what I want to say is that, well, so this Whittaker thing, this vanishes. So this is kind of the easy part. It vanishes on this L2 phi, unless, so phi has this ortho part, right? Sorry, the SL2 part rather. Excuse me. And so unless phi is trivial on SL2. So this is a simple part. This you can see locally. This was observed by Shahidi, among others. So you only are concerned with the tempered guy. So you can just say goodbye to the SL2, just parameter of the LF. And in fact, you don't need to care about the discrete spectrum. I mean the discrete non-cuspidal, because if the discrete non-cuspidal is never tempered, so forget about this. So that implies actually no, so only cuspidal part. So in other words, the L2 phi is contained in the L2 cusp. Okay. Now, the L2 phi, in as much as it makes sense, so I claim that for any such phi with trivial SL2, the space, okay, let me write it formally. So I look at all the phi in L2. I mean, I hope this is, you can distinguish. So I look at the thing where this Whittaker coefficient vanishes identically. And then I take the orthogonal complement in L2 phi. So the claim is that that's part of the conjecture, if you like, that this is irreducible. So this is the orthogonal complement in L2 phi. And this is irreducible. That's the claim. So this is part of the conjecture. In particular, non-zero. And so let's denote it by, I don't know. And that, of course, depends on the psi that I chose, but I fix once and for all. Of course, the different psi's that amounts to the action of the adjoint group that I mentioned before. And then, so the claim is that for this thing in this.
But sorry, if it's non-zero, it's automatically irreducible? Or is some multiplicity one?
Yeah. Yeah, you're right. If I have multiplicity, how do I want to say it? I mean, if I have, no, I'm sorry. I mean, this is only if I know multiplicity 1 a priori for the L2 phi, which maybe is not true.
If you know what?
If I know that this is multiplicity 3, right? Otherwise,
I see.
this is the orthogonal complement. Yeah. So actually, so this kind of definition, so Piasecki-Shapiro, again, before you were born, I'm sorry, invented this notion of, he called it something, that you look at this orthogonal complement of this, and for him it was the generic spectrum, if you like. But I mean, it's not fair because he's no longer with us, but I beg to say that this is a wrong definition, because it's only when you look inside this L2 phi that it's meaningful, because in SLN you will get into trouble because of multiplicity. So you really, I mean, so, but of course at that time there were no Arthur's conjectures. I mean, Arthur was, sorry?
What is the problem for us?
I mean, the problem is that you will get several things, and it will not, it will be kind of, from two different things, you will get kind of the diagonal thing. I mean, the Piasecki-Shapiro space is multiplicity free, but here I really want a copy for each parameter, and you will just miss it because you will get kind of diagonal in several spaces. Yeah, for SL, yeah, not for SL2 by a fluke, but for SLN. Okay, but that's maybe just a point that. Okay, so the conjecture is that it's for this space. Okay, and now it's very important.
You want to take the projections of this space to the eigencomponents.
Right, I'm really interested in each, yeah. If I have some diagonal space in the several things, that's not good enough. So this is the right space, and for this conjecture, because at least in so much as it matches with isogenies and stuff like that. So you do this kind of checkup. You cannot, of course, you cannot do E8, right? But at least some things you can do. And this is very important because so now I'm back to this thing that you see. I mean, the left-hand side depends, of course, on the realization of the representation, while the right-hand side is kind of an abstract thing. And so it really depends on the physical realization, and that's why I was so adamant about this canonical decomposition, which, however, is unrefutable because I didn't say what are the. You cannot characterize it, and that's of course a problem. But so it's a kind of second-degree conjecture. However, in many cases, the real life is better, especially if you have multiplicity 1, then you don't need to worry about this thing. And you have them at least, I don't know actually what is the exact status, but morally you certainly have them for classical groups. Of course, SO2n is not a classical group, but you can work with O2n and match it.
What's that?
SO2n is not a classical group, but you can match it with the classical group which is called O2n, and things work out nicely.
SO2n is not a classical.
No. A classical group is defined by a quadratic equation. So, okay. So what do we know about? So does this conjecture make sense? No, because I didn't put everything on the table. So this thing, don't worry too much about this. This is kind of L function attached to the motive of G, but it's much less scary than it sounds. It's basically some very explicit L factor, which depends only on G. So just for the measure considerations, so just ignore. And this thing, yeah, this of course, this is important. This is the centralizer of the image of phi in G of L. And it's finite because the parameter is discrete. And this thing, of course, it depends just on phi. I mean, you can make sense of it. Well, at least hypothetically, but you have to know that it's non-zero. This is part of the conjecture. I mean, that doesn't have a pole. So no pole, again, part of the conjecture. So it's meaningful, if you like.
There is a question. Has SP, has it been tested in some case where that uses non-abelian?
Yeah, that's a good question. So I don't know. I mean, for G2, I think the technology is there, and actually I definitely encourage somebody to do it. It does pass some tests which, yeah, no, but the simple answer is that I don't know. But G2 is a good candidate. Okay. Yeah, and as, again, for Peter, I mean, by saying this, it doesn't mean that this is kind of something that you can sweep under the carpet, just like I did. It's just some formulation, and with this you have to win, right? I mean, but that's the best I can do. Of course, you need to compute things afterwards. It's not the end of the story, but at least it gives you some framework. I mean, if you're interested in the left-hand side to begin with, right? But of course, this conjecture doesn't come out of the blue, and again, as I said, it'll be influenced by Yanis and Akshay's book, which is of course influenced by Wells-Perget and Ichino-Ikeda, etc. It's just a way to formulate. The point is that you can kind of make it very precise. And so let me just say what's known and then what we'll do next time. So it's okay for GLN and somehow compatible with isogeny. Compatible with isogeny. So it's okay for SLN and stuff like that. And let's say twisting by characters, which of course doesn't change the Fourier coefficient or the adjoint L function. And now for classical groups.
Okay means proved or?
Yeah. No, absolutely. This is, in fact, basically I explained this, but it also appears in Akshay and Yanis's book. This is kind of well understood. So for classical groups, this reservation can be, at least you can phrase things. So one can phrase it more explicitly using, I mean, the point that we really have, so I said that there should be this space, so the L2 generic stuff I can define, if you like, the direct sum of all parameters, I mean the tempered parameters of this, what I call the L2 psi phi. So there should be a meaningful space, which in the GLN case it's simply the Caspital spectrum, nothing more nor less. And for SLN it's just the restriction of the.
What's the status of the trace formula for exceptional groups? Is nobody wrote it?
I mean the stable trace formula was done for energy. The problem is, what do you compare it with? I mean, you get some formula which says that something is stable. Okay, I mean, you have to compare it, and we don't have anything to compare it to.
Besides G2s.
Besides what? Yeah, except in G2 maybe. Oh, you asked specifically for G2.
Yeah, I'm asking for an exceptional group where I know that there's a lot of work using minimal representation and other methods, but using the trace formula, which has clearly been successful for classical groups. So I'm asking, where's the difficulty in terms of using the trace formula
So
when you're not classical?
the difficulty is that you have nothing to compare it with.
It's not a twisted endoscopic group, is that the problem?
Right, E8 is not a twisted endoscopic group of any GLN, right? I mean, what? Okay, G2. Okay, maybe G2 is on the table. I don't know what's the status of G2.
In terms of the trace formula.
Okay, so the answer is I don't know.
Okay.
But then the question is whether G2 is exceptional or not. To begin with, I mean, I don't know. I mean, what's the difference?
What I'm trying to understand is the other parameters, I think, jive well when the trace formula works. That's where he came with it, and that's how it works. So when you want to say something in general, the evidence may be much. I'm just asking what is known about the trace formula in exceptional groups in terms of working with it.
Okay, but yeah, no, I don't think you can hope for anything like Arthur's book for E8. I mean, that's certainly because you don't have to start with what to. Okay, where am I? Yeah, so in this case you can. So I said that there is kind of hypothetical space, but if we don't have a way to reach it, then it's just useless, right? But for classical groups, we're in good shape because we can construct this space, what I called L2 gen psi, for any classical group, for any quasi-split classical group. And this is thanks to the work of Ginzburg, Rallis, and Sudry. So they give you a construction of this space in terms of so I'll just give an example maybe to so starting with pi on GLN a Caspidal, let's say, and with certain condition, let's say exterior square having a pole, or symmetric square, or psi, or whatnot, depends on the context, one can concoct a space, okay, sigma of pi, if you like, on the corresponding classical group, which of course, so G prime, so there is an L group, well, okay, whatever, L group homomorphism to the GLN, kind of tautological embedding, which, so think concretely, I mean, this could be like an orthogonal group and the symmetric square or the exterior square depending on parity. But this space is explicit in the so how is this constructed? This is constructed as Gelfand-Greif, so some Fourier coefficients of residues of Eisenstein series. Fourier coefficient whose stabilizer is exactly this G prime or contains G prime. Right, so the Eisenstein series is taken on a bigger classical group. So in a typical situation, let's say you start with GL2n, with exterior square having a pole, then you go up to SP or SO, let's say SO4n. So this is the Levy subgroup of a maximal parabolic, and okay, and then you take Eisenstein series. The constant term is dictated by Ls pi. In this case, I guess Ls pi exterior square, if I'm not mistaken.
And the Eisenstein series is on without Levy.
Right. So Eisenstein series on G induced from so pi twisted by determinant with the S, which is yeah, that's on the Levy, and it has a pole. It has a pole.
And its constant term is probably an elementary.
Well, say that again.
This Eisenstein series, which you're analytically continuing
Uh-huh.
in order to get the pole,
Sure.
is an elementary Eisenstein series in the sense that its constant term
So-
along probably the same.
So its constant term is this L function.
Okay, which you know about.
Right. I know about this, but yeah.
I'm just want to kind of nail exactly what aspect of the theory of Eisenstein series is.
Well, we need basically the full force. I mean, we need to know where is the pole. But I mean, okay, that's kind of it's negotiable. Let me first say what's the. But implicit here that there is a pole, and then so now you have an automorphic form on SO4n, this residual Eisenstein series. Take a residue. But things are relatively understood here, and then you just take Fourier coefficient down to whose stabilizer is SO2n plus 1. So in the case n equals 2, which of course would be very, I mean, n equals, yeah, I guess n equals 1 would be the completely redundant case, but just to fix ideas. So you take GL2 to SO4, well, SO4 is basically, I mean, ignoring isogenes, it's just GL2, and what you do here is basically just take constant function on the GL2 by taking a residue, and you just restrict to GL2. Okay, that's not terribly interesting, but just to show you. And then in general, you take some Fourier coefficient whose stabilizer is is this. So there is some kind of starting of Whittaker part, and then you just restrict to the. I mean, then you take something which is. I mean, the vector is not. I mean, it's an isotropic vector, so the stabilizer is a smaller SO. That's why you change the parity.
So what did you just say?
Sorry?
What did you just say? I couldn't hear.
Yeah. Well, I said that I take a Fourier coefficient of this automorphic form whose stabilizer is a smaller orthogonal group with a different parity. But morally, I'm just restricting from bigger SO to smaller SO, but I also take some Fourier coefficient.
Is this some? It's not a Levy, right?
No, it's not a Levy. So
So sorry, you're taking a residue of the Eisenstein series first.
yeah,
And then you're restricting to the subgroup.
I don't restrict. I take a Fourier coefficient.
Right, I agree. And the claim then is that that's
The claim so this is my construction. I mean, I wasn't very explicit, but this is my V sigma pi. I mean, this is my G prime in this case, and this is how they achieve the remarkable construction. I start with a Kasparov representation on GL2n. I take a Cas form here, but I take the Eisenstein series induced from a section on this Cas form. Of course, I take all the sections at the end. Okay, let's do first thing first. I mean, this is just the construction. Okay, so I start from my induced space, and then this construction using Fourier coefficient of the residue give me some space. So the image of this, by definition, is this, what I call V sigma pi. Okay, so I get some space of functions, but of course the main thing is that this is irreducible, and of course that it matches with functoriality. So this will lift.
one thing is whether it's
So sigma pi will lift to pi.
because it's non-zero.
And non-zero, right on. Well, I said irreducible. Of course it's not zero because it's irreducible. Okay. Okay, anyways. So, but
An inner product formula for this like that.
right. So that's of course.
What comes up in that? Which there's some other alpha.
Right. So what comes up is an L function. So we of course we'll use it. I mean, so the short story is that there is an inner product, and you can compute. And this will be generic also. So there are many statements here, but so the final statement is that this sum over this V sigma pi is exactly, or at least it's a candidate for this L2 generic psi, what I said. Of course, everything depends here secretly on the choice of psi. And I mean, whether or not it's a theorem or not, you can still use it as a working definition for your conjecture. So now at least you can, yeah, but of course, I missed one important point, is that you can start not with just one pi, you can actually start with k of them distinct. So this is on GL2 and I, which sum up to n. And you can do the same construction. Now it's an Eisenstein series, not for a maximal parabolic, but you still take this, just the limit, I mean, if you like, the iterated residue, or how do you want to call it. So the same thing will hold, because locally the theory will be the same. And so you can do it for that, and that's important.
Sorry, Erez, which L function comes up in the inner product formula?
Okay, so okay, I don't want to write.
Before you compute that, in their work,
Yeah.
what's the summary of their work? They started with summing of GL and making it transfer to the correct classical group. They actually achieved that, and there's some generic assumption. Is that the point?
So
Yeah.
So what I described here is the construction. So you can start with pi or several pi's, according to your wish. And what you get here is a space of functions which is irreducible, generic. And now to prove actually that you get everything, that's a different story.
Okay.
But
But you get something for the starting pi.
mhm. The starting pi is
It's
just,
just-
yeah, I should have said that. It's a,
It's got some
so
self-image.
this has a pole.
Yeah, okay, that's the only assumption.
Right, but it's a Caspar thing on GL2n, yeah. And if you start with several, each one has to have this pole, and they should be distinct. And eventually, that should give you everything. Well, with the converse theorem and Shahidi, Kogel, Kim, Shapiro, then you can actually get that. But at this stage, actually, the theory is somehow not entirely symmetric. I mean, it's not self-contained. But anyways, it is enough to phrase the conjecture. Okay, so I don't want to take too long. But this will be the starting point of next time. So next time I will kind of revisit this and then explain what things mean precisely in this case and how you can make sense of the conjecture. In fact, prove it using the construction. We use it heavily. And also I will relate it locally to the formal degree. Okay, I think I should stop here.